Hi, everybody. Welcome back to our live stream from Deep Dives. My name is Johannes Verwijnen. I'm a full-time instructor on all of the hyperscalers, and I've got a pretty convincing background as a developer, analytics, big data, machine learning, just name it. And with me, I have my friend, Mikko Nieminen, or at least on-off friend. He hates me every now and then as well. And you've got
currently
similar background.
on. I have a similar background as Johannes. My name is Mikko Nieminen, and I would describe my background as a software developer / architect for the past 25 years or so. And a full-time instructor nowadays.
Yeah, exactly. We're both instructors, so if you take any courses, you might see us there. And today's topic is databases. So the title is like databases. And what I wanted to talk about is, again, how things have changed. Kind of what is different from a software developer point of view. What has changed during the past 30 years of databases?
Only the 30 years.
Yeah, we can go a little bit further back.
We can go a little bit further back.
Yeah, as well. But the interesting part has happened during the past 30 or 20-ish.
From our point of view, yes.
Yes, yeah. So first of all, for those of you who don't know, what is a database? What is a database? It's a collection of structured data. This is in the Wikipedia page that we're viewing right here. And what we mean by structured data is that there are often what we would call columns and rows of data. So you can think of like an Excel sheet. However, the actual cells in the Excel sheet are well defined. So the Excel sheet itself might be not a strict database as what we're actually meaning here with, for example, a relational database. And so databases kind of started off back in the 50s and 60s as IT in general. And kind of the idea here was that we had data, like records of data, and we wanted to have an efficient way of saving that data. And then, of course, also efficient ways to query that database to find certain results. And as an example, we could use something like a staff database, right? So a database where we have the people who work for the company, maybe their salary information or absence information, that kind of stuff. And then that database could be used by the payroll department to calculate our salaries or how many holidays we have per year or whatever. And one kind of interesting thing that happened with databases fairly early on was this idea of a relational database. Do you want to give us a quick intro into your understanding of relational database compared to other databases?
Well, my background is with relational databases. Like my formal education in the university, and before that we dealt only with relational databases. We actually went quite deep into the details of how they work. And also from my work life, everything was done using relational databases. And in that sense, it kind of blurs the background or the history of where we come from. The other solutions, different kinds of databases before relational databases, and the file-based storage, which was
exactly.
I remember one of my colleagues talking to me. He had a long beard. talking to me about how those were really efficient, and I was not convinced, and he proved me wrong, of course. But that's like the background. I'm very, very, very biased towards relational databases. And now,
Yeah.
now, if you ask for a formal description what a relational database is, then I don't even have one. I've been using them for so long time that it's kind of natural. I know how to use them. I know how they work in not only in theory, but well, that's for the other way around. Not only in practice, but a little bit of the theory as well. And I know in practice how to make them fast in the most common use cases. Of course, there are situations where you need some experts there to really fine tune something.
Yeah,
But
this is of course
that's actually my understanding of the relational databases. Because of course I forgot what we were taught in the university. I don't have a proper description of what they are. I just know that we have tables, and we have a way of accessing the tables and the data in the tables, and there are relationships between the items in different tables, and the database engine enforces those relationships, makes it sure that the data is what it should be. For example, that there are no, well, that kind of, well, from practical point of view, that's what I would say.
That's exactly it. That's exactly it. And I think a lot of people with a developer background share your view that relational databases are databases, right? That's kind of, especially if we've been around for tens of years, that's the majority of your persistence data is going to be relational databases, just the way it works.
And there's
that's why I wanted to talk about it.
One thing more, my older colleagues who were even older than I am, they were thinking about the internal structure of the database and the internal the physical machine as well. How many disk surfaces there were when they were making a new database? What kind of hardware they had in the background? And I kind of jumped into the databases that late that I didn't have to bother. I didn't have to worry about those things. But
Exactly.
people before me, they really went into the details.
Yeah.
And so in that sense, I'm already one of those developers who have been using databases as kind of just a service, but not completely, because I started, of course, on the on-prem side.
Yeah. So I just kind of to interject a little bit, I remember creating non-relational databases myself for storing kind of all kinds of data. This kind of existed in the late 80s and early 90s. You had these, customer databases or product databases. Even Mac had this cool.
Did you talk about records, or what was the unit?
It basically, you would create a data structure and then just have a way of writing that onto disk, and then you would read it when you would want to, right? And Mac even had this cool program called HyperCard that was this kind of a general card-based database, but definitely not relational. So what is actually a relational database? So first of all, we can thank one person or mostly thank one person for introducing us to a relational model for database management. And that's Edgar Cod. And this same person we can also thank for the normalization of data, right? So he actually got a Turing Award for this work. The Turing Award is basically the Nobel of computer science. And he did all of this in the 60s. And basically, a lot of publications, a lot of interesting stuff. The thing that most people know about is the normalization theory. So we very often say that we want our data to be third, what is it called? 3NF. Third normal form, right? And third normal form officially is like second normal form plus something removed. In general, in 2 minutes, what does normal form mean? Well, it means that if we have any kind of duplicate data, then instead of writing that in duplicate, we would refer to it from a different table, right? So if we have like a book table where we would have authors, right? Then in general, we could think that an author could have actually written multiple books, right? So then this column here about the author of books shouldn't actually be a column because we might repeat the same value over and over again. So instead of having the author here, what we will actually do is we would have authors in their own table and then just refer to that author using an ID. And this, the motivation for this originally was actually about space, because back in the 60s, storage space was really, 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 really expensive. It was really, a hard drive would be the size of a living room, right? So it's like really difficult to store anything. So instead of using, who knows how many bytes to store an author name, we could just use an 8-bit integer to refer to that author, hoping, of course, that we don't have more than 255 of them. but still, same thing for like stuff like format, right? Instead of having hardcover, ebook, paperback in here, we just have IDs 0, 1, 2, and then we have a separate table where we then define what that ID actually consists of. And then, of course, some of the data still needs to be in the original format. So something like a price that varies per record, right? So it probably should be there in numerical format instead of a reference. So third normal form is kind of normally the target state of a relational database. I don't go into details how third normal
if I may
form
add here, this is so, like, if the database is written in any other way, for me it looks wrong, incorrect.
Yeah,
that's so like hammered into my DNA that this is the way databases should be like used.
yeah,
Because basically that's how you did it. Not anymore though. And if you had some really, like, there are situations where you didn't do it that way, but if it's done in a different way, it looks incorrect to my eyes. Even now.
Yeah, and there are some benefits from this.
Yeah.
So
not only the storage size, but maybe the speed as well.
Yeah, another benefit in here is that if, let's say, if a publisher changes their name from A-Press to something else, then we only need to update that in one single place. However, that is also a bit of a problem. Like yes. What if we want
you lose the history
to refer to the name in a historical way? Yep. And then if we change it everywhere, right? So but yeah, that's basically what a relational database is, or what a relational data model is. And the relational database management system enforces these models, right? So we can actually define in the table that this particular column refers to an ID in a different table. And then the database management system can enforce that relationship. So for example, it won't allow us to delete anything from the author table if we have a reference to the author in a book table, right? So we're making sure that these links don't get broken. And then, of course, if we want to get human readable data out of the table, that means that we need to do lots of joins to be able to fetch those individual pieces of information from different tables. And that's basically what a database management system is optimized to do nowadays, is to effectively do these joins of data for making it possible for us to query the database. But yeah, so that's kind of the history. So we're kind of fast forwarding through the 60s and 70s and 80s
That, yeah.
to when the internet happened. Let's call it that. Like that's where we are. So
Then the problem started.
Yeah. So how did software development work like in the late 90s, early 2000s, when you would have a project that would contain, dynamic information that would need to be retrieved from a database? Did you ever get asked, what kind of database would you want for your project?
Quite often, the database was decided already for me. So maybe the organization, the place where I worked, or the client, they already had a database system. Let's use the classic, the Oracle example. They had an Oracle database already. And that's quite often. And then you were using that specific database, or IBM DB2 or something like that. Then you were using that. No questions. and it worked because everybody were doing their project like that. Everybody was used to that. You knew that, okay, we don't know the exact database, but we are hopefully not using too much of the specific features of the database, but trying to generate more like all-purpose. For example, the queries, you would try to make them all-purpose queries, so that they're not that dependent on the database. But to be fair, we never changed any databases. So once you chose something, or something was given to you that, okay, you're going to use this database X, then the whole project was stuck with that. It never got changed. And even, but from the maintenance point of view, it's kind of a good idea not to rely too much on the super trickery of the database or something like that. In the long run, it's easier to maintain when you are doing straightforward, if the workloads are such that you don't need to optimize all in the optimization department.
Yeah.
That's my attitude towards simple solution.
Yeah, I would kind of say that the database management system was pre-defined based on the customers. I would claim that there were kind of two reasons why we would use a specific database. The first one would be the customer's experience in operating that database management system. So they would have like a DBA, a database administrator, who would know how to run that database, right? So maybe it was Oracle, maybe it was DB2, whatever it was the one thing that they knew. So introducing a new brand of database would be problematic for them because they wouldn't have the know-how in-house. And back then, there wasn't very often a convincing argument why one would need to pick another database. And very often, we would actually just get a new database inside an existing database management system, right? So in the same server, in the same database management system, there would be other databases logically isolated, and we would just kind of be added to that.
Yep.
Sounds familiar. Sorry?
Sounds familiar.
Yeah. The other reason, except for just know-how of operations, would be basically economics, right? So there would be already this database management system, which usually was fairly expensive from the licensing point of view. So there was already money spent into a database management system. So then it kind of makes sense to put the project to use that instead of investing into more databases. But then that of course becomes a vicious cycle, because then the more projects you have running on that database, the more quickly you need to add more capacity to it. And then
but then again, then you get to use the same database instead of trying to run three different database engines. You're running one, and you need only handful of experts, not just one, because if you lose that one person, you're in big trouble. But just handful of people who are able to then run the whole show from the management point of view.
So in my experience, our kind of the options that we saw back then were either that we would run on top of a enterprise database management system, something like Oracle or DB2 or something, or then we would deploy our software together with an open source database solution. Back then, probably mostly MySQL.
When was MySQL introduced? When was it a real alternative?
We have the internet, so let's ask it.
Yeah. I'm on it.
Fairly early on.
1995, first version.
Yeah, 1995. There is a fun trivia with regards to MySQL. So as it is at least partially Finnish. So Morten Mikkelsson, a Finnish, how would you call it, a tech evangelist, was one of the founders of MySQL. But yeah, so this was, even though the company was Swedish, but we still take pride over the product as Finns. But yeah, so MySQL was kind of a lightweight relational database engine that had some non-standard SQL functionalities that made things easy, like an auto-incrementing ID column, primary key column. That was kind of, for me, one of the best features ever. But there's also plenty of other things, and that kind of made it fairly popular as an option for deploying. And then because it was open source, it was also practically free to deploy. So we used a lot of that. Since then, what is your opinion? What is the number one database engine now?
For me,
yeah.
If I just have to choose something and it's a relational database that we're building, I'll always choose MySQL.
Okay.
Yeah. Because it's, again, one of those things that I've been working with it for so long, and I'm kind of stuck. It's like you choose a product from your grocery store. You choose the same product that you've been using for a long time. So there's no like technical reason for me to choose that, but it feels, well, let's put it this way, it's usually not a completely incorrect choice if you choose MySQL. And most of the projects that I've been working with in the past, like in the early internet days, we didn't have that much load with the databases. There weren't that many users. There weren't millions of users accessing the same program or system at the same time. And these very straightforward solutions were just completely fine, because it was about business logic, not about the scalability. Most of the time, it was about the business logic. In those cases where I've been working with, that can be, of course, different for other people, but for me, it was mostly about the challenge was the business logic, not the speed of the storage layer.
Yeah. So MySQL it has a reputation of maybe not being so professional. And the reason for that is actually not MySQL itself. It's the storage engine, MyISAM, was used like over 15 years ago. That's kind of where the bad rap comes from. So there was a new storage system released in 2010 called InnoDB, which is much better, and it actually allows MySQL to be working in a proper way. So kind of the old storage engine got into trouble, especially with those kind of situations that you've mentioned. If you have a lot of simultaneous users, then the table locking wouldn't work correctly, and there are some restrictions with regards to transaction support in that. And then kind of back in the days when you needed to have a proper open source database, you would choose Postgres. And the Postgres is a totally different open source engine. Let me just open it up here. And it was kind of the fully fledged open source database. It has all of those consistency guarantees and so on. It's roughly similarly aged than MySQL. So it's originally from 1996, but it was inherently more difficult to use. It was like strict with the SQL commands in ways that MySQL didn't care about. So when moving from MySQL to Postgres for the first time, I was scared. I was like, what is this? Why does nothing work? I thought I was doing standard SQL, but then I saw that I actually wasn't. That there were lots of shortcuts in MySQL that was used. And Postgres is actually really, really, really popular nowadays, as it has actually been used for a lot of the data warehousing products as the front end. So this includes like AWS Redshift, right? With Redshift, the front end, basically the JDBC connection endpoint that you connect to, and the query parser and so on, those are all coming from Postgres. This is also true for other data warehouse instances. For example, Greenplum is a kind of medium-sized data warehouse, which also uses Postgres as the front end. So it is a kind of more serious, if one can say so, way to do relational databases. And these two, MySQL and Postgres, are also the two open source database engines that are available in the cloud, right? So if you go to any of the cloud vendors and you want to get a database product up as a kind of a platform as a service, I guess, then you would have these options, and possibly also MariaDB, which is a kind of a new incarnation of MySQL by the same people as well. So those are open source options. In addition to these, we have, of course, also the commercial options like Oracle, as has been mentioned, IBM DB2, Microsoft SQL Server, maybe something else still out there. I guess that's pretty much 99% of the market. Right?
DB2 was the first database that I was using.
Yeah,
I was blessed with that.
Yeah.
I don't have any recollection of the project, even what it was, but I remember that DB2 was the first one.
So we have relational databases. We talked a little bit about the relational model and that it has some advantages. What other advantages do you think that relational databases have over some other databases that we might be talking about soon?
Well, if you consider the background, how well they are known, how widely they are used, then that's one benefit. You have
so
people
SQL, basically, that's what you mean, right? SQL.
Yeah.
Or kind of generally knowing how to create the database. How to
I mean, like not writing SQL, but like the idea of having a database, and that, so people are comfortable with that, and so that's one. I lost the train of thought here. So you have people who are familiar with them, and you were asking what are the benefits, or
what other benefits? Yeah.
Well, they are general purpose databases. They can be used in many, many, many different kinds of situations. And they are not the optimum solution for every use case, but almost any of the following databases that we're going to cover can be implemented also as a relational database.
Yeah.
Which kind of makes it hard to adopt new ones because the old one kind of works until it doesn't anymore, until the performance, for example, is not there anymore. But they are these relational databases are good for that reason, that they can be used for very different kinds of situations.
Yeah,
I
would kind of point out the consistency guarantees. So ACID consistency. So if your use case is such that you need to have ACID consistency, then defaulting to a relational database might be a good idea, right? Because it comes built in, so you don't have to worry about it too much. Another thing would be
so what does it mean to have that ACID, to have those properties? When you write something to the database, it's there, and whoever is reading from the database gets the same result. If it's accepted by the database, the new data, then you can read it from there as well. So atomicity, consistency, durability.
In my classes, I use just a little bit different language for the definition. So what I say is that if you try to read from a database, then what you will read from the database will be consistent with any write to that database that has started before your read. So even if a write is coming into the database, then immediately after that write has been started to be processed, you try to read. Then the database will make sure that the write will go through first before allowing the read to actually return anything. And this might be important if you're handling stuff like, I don't know, bank account balances.
Usually you want that to be consistent.
Exactly.
But also it makes it, in some cases, if your writes are really slow, then somebody has to wait, or a lot of processes have to wait for that write to complete. So there are challenges with that in some cases. In some cases, it doesn't matter.
But that's a good thing. So we have ACID consistency. Now, what's the bad thing that comes with ACID consistency in relational databases?
Well, are we talking about speed?
Yeah, in a way. So when we have ACID consistency, can we do that in a distributed way?
It's really difficult or impossible. With I have to be very careful with my words.
Yeah.
So I gave you two options and then you choose the one. Come again?
Yeah, but like in general, relational databases are designed in such a way that they're monolithic, right? So there is,
when it comes to writing.
Yeah, specifically when it comes to writing. Let's take reads away for a second, because we want to have ACID consistency. So just talk about the writes. So when we have ACID consistency, that basically means that there needs to be one place only where we're doing writing, because that way we can guarantee that everybody else is waiting for that write to finish. In theory, we could do this in a distributed way. The problem is called distributed locking, but it's just so difficult and so slow and so unpredictable that we have relational databases where we want to have ACID consistency almost always. We don't do it in a distributed way. We just have a single computer that in memory can create these table locks or partial locks to ensure that nobody is reading from the database while we are writing to it, and then thus ensuring consistency. And I'm simplifying a little bit here, so please.
And when it comes always at this point, somebody says that about read scaling, and if you have read replicas, in general, they are replicated asynchronously.
Yeah,
which
in general,
allows you to read from the read replica while the write is happening. But there's no guarantee that the read replica has the latest information.
and there
It's
are
like behind.
multi write endpoint systems that make multiple nodes for writing possible, but it's not the rule. It's the
in general.
Yeah, in general, what I'm saying is true. So what is the
That's
problem?
how I always start the discussion, that in general,
yeah,
it goes like this, because there are some not so common systems and some enterprise level solutions, but just to keep it simple, this is the way this is the way it goes.
Yeah. So what is the problem that we get into when we're having a monolithic database?
Scaling.
Right? Scaling. So first of all, scaling and high availability themselves are problematic because you can't just move traffic over to a different database. Right? You need to, at some point, say that, okay, now our old database has done its last write, and then we move things over to a new, maybe bigger database instance, right? And that cannot be an immediate switchover. We need to make sure that all of the data that has been written to the original database is also replicated in the new version.
And so there's of course you do that scaling, but you don't want to do that like several times per day, for example.
Yeah, there's always going to be some downtime. Could be just
problem there.
A couple of minutes. Could be bearable, totally okay, but still. And that's kind of one problem. And then the second problem is that if we're going internet scale, right? So instead of talking about hundreds of thousands of customers, we start to talk about tens of millions of customers that are using our database.
Trying to open a connection to the same database.
Yeah. And then we tend to get into trouble, because even though we can, get bigger and bigger instances to run our databases, at some point we are running on the biggest possible instance. And then what's next? What happens next? And that's kind of the problem.
Yeah, and there are, of course, there has been solutions for this way back when the database, on the hardware level, the hardware wasn't, well, it wasn't that capable as it's nowadays. So you did already do, with relational databases, you did do sharding, for example, or partitioning, whatever you call that. That's and those were, when I was quite young at the time, and it was someone else who said that, okay, come on, we have to do it this way. There's just not enough capacity. For example, all the historical data is automatically not part of your queries.
But if you do sharding, then if you need to do cross-shard joins, that's going to be problematic. So you
go ahead.
Yeah, you kind of can't take the general use case where we want to join tables randomly in a relational database and then just say that we're going to fix things by sharding. It just doesn't.
Yeah. But these were the situations where you had experts and they really understood the use cases, and they know that, hey, you're not going to use this old data anymore. So you needed that expertise to. Of course, nowadays that's not a problem anymore. Well, we should have that expertise anyway, but you couldn't solve everything on the hardware level, definitely not, because the hardware just didn't or wasn't capable enough. And it's not now. It's the same thing nowadays. You just, the limits are just so much higher. But still, if you have tens of millions of customers accessing the same data at the same time, there are things that you can do. You can do caching and you can do connection pooling and all kinds of things in the middle. But sooner or later, you will hit the limits of a relational database in general.
Exactly.
In general.
So what are we going to do, right? So let's say we're Amazon.com and we have lots of online customers, and we want to have a database with, for example, the contents of shopping carts, right? So what do we do? Well, you said that we can do sharding, right? So or partitioning. So what that basically means is that we split the data over multiple servers, and then we do that in a predictable way, so that when a query comes in, we kind of know which server to go to find the data that we want to query. Again, I'm trying to simplify here. So, but if we do this, then we create basically a distributed system. And what we lose, again, generally, here is we lose ACID consistency, right? So we can choose to create a database that can scale by partitioning data if we, as a kind of a counter offering, give up on the requirements of having ACID consistency. Or maybe let's say that we're moving the handling of ACID consistency somewhere else. That's probably the better way of saying that. So these kinds of databases are called NoSQL databases, right? So
and before we go even there, the thing that you really have to do at this point is to really understand what are the requirements from your system, what are the use cases, and then really think before you choose your database. Think about what are the potential limitations and how many users you have and all that.
Yeah, we're going to go a little bit over time today. So this discussion is actually going to go a little bit deeper. But we will return back to exactly that question in a short while. So what we have here is the Wikipedia page for NoSQL databases. What does NoSQL mean in your opinion?
In my opinion,
yeah,
and this is again from a guy who has very strong background in the SQL or relational databases. It's always, do we really want to go there? So that's the initial reaction was always like that in the past. So first of all, you can't make your queries the same way that you used to do.
Mm-hmm.
You cannot just afterwards choose that, hey, I want to query that and I want to query this. You have to do more planning beforehand.
Yep.
And then also the data is stored in a different way. These are my initial things that I like intuitively. This is what I'm thinking. Maybe we are storing all the data. Maybe we had just one table, and everything is, for example, for an author, all the books are stored in one record. If we just call it a record for the time being, everything is stored potentially in one record. So if you have a very popular author, then you have lots of books, but you can access all the books from the same record, which is completely upside down what we had with relational databases.
Exactly. So
you don't have to do it that way, but it's one approach. And this is why it has been very difficult for me to adopt to these new approaches, because it's upside down and it takes time for old people like us to change. And that's actually something that we need to think about when we are trying to convince other people to at least look at these other databases.
Yeah,
because I know for most people, the initial reaction is that, well, we don't do things that way, so we just skip this. I don't know how you feel about that.
I kind of agree that there should be a reason. We'll talk about polyglot persistence in a second, but for now, let's just kind of go past that reasoning. But there needs to be some kind of reason why you would choose a NoSQL database. It very often is not kind of the first default option that you would go with. But there are very good use cases for NoSQL databases, and there are different kinds. But what is in common with them is actually not that you can't use SQL with them. Nowadays, there are SQL clients or SQL-like clients for NoSQL databases. Another name that some people use is that it's a non-relational database, and that's not true either. You can still do relations with NoSQL
But
databases.
the engine is not enforcing them.
Exactly, the engine is usually it's kind of a developer problem here. So in general, kind of the most used type of a NoSQL database would be basically a key value store. That's a key value database. That's kind of what we're looking at. And for a developer who's totally new to this stuff, the easiest way for me to explain what a key value database is just think of it as being a hash table or a hash map, where you have some data that you can access based on a key. And then, of course, this is not an in-memory data structure, rather it is persistent, but it's done by the persistence is handled by the database engine. But the access pattern to the data is the same as it would be with a hash table or a hash map. So your options are basically only to either know the key that you need to access the data, or then list through all of the data, or at least all of the keys, right? Be able
Which
to.
might be a problem if you have petabytes of data.
Yes, exactly.
So then,
so that already
should something else.
That should already ring some alarm bells. That now actually the design criteria for a key value database should be based on the access patterns to that database. So kind of if you don't know the key, then you can't get the data. So you need to, instead of creating a database structure based on the contents of the data or the structure of the data, you need to design the database based on how you want to access the data instead. Kind of things that you would do as an afterthought with relational databases. In a relational database, you kind of add indexes based on access patterns if needed. Whereas
by the way, that also depends on how strict the development processes are. I've been, for example, working with let's say banking environment, and we were using like the strictest waterfall method of creating software, and in those cases, you really designed the software and you knew most of the use cases beforehand before you actually started to do anything.
Which is what you would
nowadays
need. Which is what you would need for a key value database.
Yeah, exactly.
So kind of one way of thinking about choosing between key value databases and relational databases is that with relational databases, you have that freedom of querying, so that you kind of don't need to know all of the queries that are going to be used on the database beforehand. Rather, you can just type in some SQL and then it will work. Whereas with a key value database, you kind of need to know how you're going to access the data, and you can't, at least effectively, access the data in any free way afterwards, right? And it might also be difficult to change the architecture of your database tables. So that's kind of a high-level view of key value databases. There are other database types.
Before you go there, for us, it's you said that okay, there needs to be a reason to choose a NoSQL database, but for younger people, I would say it could be the other way around, that there needs to be a reason why you would choose a relational database. If they are more familiar with NoSQL databases, then maybe that's like the go-to solution.
Yeah,
or it might change in the future.
My point here would be that those people would most likely use a document database. That's kind of what they mean by a NoSQL database, not necessarily a key value one. So a document database, I guess the best known option here is MongoDB, and it's really handy for specific use cases like handling user data. Like if you have an online system and you want to have some kind of an object that has all of the information about your user, including like what they've done on your on your website, then just creating a document based on that is probably the easiest way to approach it. And then this might very often be the first thing that people choose when choosing a NoSQL database, especially specifically for newer developers that just need some storage for their stuff. Then instead of a relational database, a document-oriented database might be easier to start off with.
And this changes over time when we start to think about like storing information and not just we need a database. If we really just need to store data and not we don't need the database. We need a way to store data. And then,
So you remember early document databases, Lotus Notes?
Unfortunately, yes.
So document databases are by no mean a new thing, right? It's just people actually used to even create online software using Domino as the background, which is the database engine that Lotus Notes use.
I remember integrating. We had a project where we had to integrate with Lotus Notes.
Yeah. So kind of, it's nothing new. However, it's much more approachable nowadays. And document databases do all kinds of nice things. Like they can do automatic indexing, for example. So
of the content.
So if you have a use case where you actually want to query data based on a specific field in a document, then you can just ask the document database to create an index based on that to make it fast to access. You don't really need to know how things work in the background. Whereas with a key value database, it's a little bit more involved. It's a little bit more difficult to add new use cases compared to document databases. But so this is probably best known for new developers using MongoDB, but just kind of to let everybody know that this is actually nothing totally new. And then we have more interesting databases like triple stores or graph databases. Again, a lot of like a document database can be implemented using a key value store. That's pretty simple to do. Similarly, a graph database can be implemented using a triple store. If you're using RDF.
Or a relational database.
But then you're talking about really complicated SQL queries.
Yeah, definitely. But the challenge here is that because relational databases are such all-purpose databases, you can create graphs using that.
Yeah.
And that's completely okay until you have the huge amount of data, and then you're lost. Then nothing is efficient anymore.
So what is a graph
database? Come again?
What is a graph database?
What is a graph?
What is a graph?
That's a good question. You could draw a few lines there just to show a connection of. Let's say let's use Facebook as an example. Oh, thank you for that. That's a very simple graph. But let's use Facebook as an example. You have friends, and your friends have friends, and some of them are the same friends as you have, and that basically forms a graph of connection of different entities and then there are some properties which belong to the entity themselves, and then the connection might have properties as well. For example, when did you meet, or what is the relationship between these two entities? Like they are friends, or they are married, or enemies, or whatever. And that's like a graph.
Yeah, exactly. And this is, of course, like doing simple queries on a graph is trivial to implement using any kind of database. Like if we have, let's talk about social network. If we want to list all of the friends of Mikko,
Trivial.
it's not difficult to do. But what if you want to find out in the social graph how many steps away from Mikko is the first person who has a friend with the name of Jean? That's really difficult to implement as a query in SQL, right? And that's kind of where the graph databases and specifically the programming frameworks for those graph databases come
And,
out. Because,
and then when you expand that a little bit, and not only is the query complex, the data volume is huge, and the amount of queries that come in. What if instead of having hundreds of queries per second, you have millions of queries per second?
yeah, that's what it really
Again, you're lost
becomes.
unless you have the correct database there.
Yeah, so with the graph database, the idea is that kind of if your problem that you're trying to solve is graph based, then you can use a graph database, kind of taking away the tediousness of implementing it yourself using a SQL database or a key value database, right? So it's kind of easier to use somebody else's expertise in figuring out how a graph should be stored and then how we can access it.
And they know the algorithms that they should be using when you're making certain kind of query and so on.
Exactly.
But you could do yourself, but why would you do that? You're
Why
going
would
to spend a few years just
exactly?
optimizing
So,
your.
so why do you use a relational database? You could just do it yourself.
Yeah, exactly.
Right? But yeah, that's the idea with graph databases. And like I said, kind of depending on the model, there are a couple of different models of how graphs can be created. An RDF graph could just be again in a triple store database, and then we actually have a triple store database as one of the examples of NoSQL databases in here as well. And again, a triple store is really simple to implement using a relational database or a key value database. But then generating the higher level queries is what is really problematic here. So that should kind of give us the three main NoSQL database types. There are more, but it's starting to become less and less common and or interesting to go through the edge cases. So let's kind of stop here. And now let's go to the idea of polyglot persistence. This is a term that I like a lot. So what does polyglot persistence really mean? Well, it means that instead of doing what we have been doing since the 90s, where we just would be given a relational database and told to store your data there, what if we could actually choose the persistence layer based on what our application needs, right? So instead of trying to work with the tools that exist in the organization, let's pick the best option for the application itself. And now, this would not be really interesting if we would be doing monolithic applications, because in a monolithic application, you have a lot of different use cases that are using data in different ways. So it's fairly easy to go towards a generic database engine, which is really what a relational database engine is, right? So easy to choose a relational database if you have all kinds of different use cases. But nowadays, one of the architecture models that we have available to us in the cloud is microservices. And then microservices have very specific use cases. And there it starts to become interesting that, if your microservice is a product search engine, then does it really make sense to have that data in a relational database? Or could there be a different persistence layer that is specialized for that specific use case? And then we start to get benefits from being able to use, or it could be, social media as well, right? You could have all of your user data in a relational database, but then only the connections between users would be in a graph database, and making these kind of complex queries easier to write.
And that's something that really, again, with people with a strong background regarding relational databases, it's difficult to think that you have other data stores than just one, and that's changing, of course. And for people who have been in the field for less time, then they are, of course, faster to adopt to this. But the idea of having these different data stores inside the same application or the project, then it's a hard thing for those who have been doing one way for their whole career.
Yeah, and this actually is only really possible thanks to the cloud. I've been thinking about this for a while, because in a traditional environment, we couldn't use polyglot persistence. And the reason for that is just because we don't have the in-house expertise. Like if I would go to a big enterprise and say that my software, I would really want to use a key value store for this, and then they're going to be like, well, we don't have any of those, right? We've got our Oracle here, so use that. But with the cloud, we have a lot of these services available that require very little operational knowledge and kind of administrative workloads. So if we use these cloud-based kind of higher level services, then we don't really need to have that much expertise in how to run these different databases in-house anymore. So, and then the other thing that and the other thing that we have in the cloud is that the unit sizes are much smaller. Like we can create a really, really, really small instance to run a database for just a single microservice. Whereas, purchasing a physical server of that size would maybe not even be possible. It would be like your on-prem environment. What is your on-prem environment again?
Oh, Raspberry Pi.
Yeah, right. The Raspberry Pi
small
size. Yeah. Right. So we could do that in the cloud. We could get a really small instance and then run our
and of course you have to find a balance there as well, because if you have just thousands of microservices and every one of them has, or let's just keep it, hundreds of microservices, and every one of them has a different kind of a database or data store, then, and this is my favorite topic, how about the maintenance? How do you maintain that? So it becomes difficult. Of course, you have to find a balance there. If nothing else, then limiting the available options. That's my opinion. You might think this a little bit differently, like that everybody should be able to choose whatever they want. But I believe that there should be some limitation.
I'm a DevOps idealist, right? So yeah.
I'm more into the practicalities.
In case you are like Netflix or Amazon or Microsoft, one of these big companies, then you should have this one team for each microservice structure in your organization. And then that team is responsible for whatever persistence layer they have chosen. And they will take care of it, right? So there is it's distributed administration instead of centralized. But that's, of course, not necessarily an option in a lot of organizations that are differently structured. So and then you need to figure something else out.
Some balance there. Yeah.
That's kind of
we agree on something, Johannes.
Yeah,
we agree on
something. We actually agree on many things. We just approach it from different directions.
Yeah. That's true.
All right. So that's a lot about databases.
Maybe we have another session regarding the rest of the purpose-built databases that we have not covered here.
We could have a separate session on analytics. And then, because a lot of the things that you're mentioning have actually to do with analytics.
Yep.
Instead of kind of a transactional use case. So we could have another session on analytics, but probably not the next one, because we don't want to bore viewers who are not interested in databases at all. So let's figure out a topic for the next session. It's going to be something else than analytics. It could actually be 2023 in review. That could be an interesting kind of a very high level view of what happened this year. And then during the next stream, it's going to be last year.
Yeah. It will be, yeah, it's now 30th of December.
Yeah. So probably we're going to go with that. We went a little bit over time this time, but
not a catastrophe, I would say.
Not a catastrophe. Yeah, we can still work with this.
We try to keep it just a little bit under an hour or so.
Yeah. In general, I'm kind of proud. We did go through quite a lot of stuff in the hour, so I think we did good. But yeah, I think we need to end the session this time. Again, thanks to anybody who's been viewing or listening. We've added a couple of targets for the stream. So besides YouTube, it's now also available on Twitch and on X, previously known as Twitter. The recording should be available on those platforms as well. And then we are going to, again, do an edited recording for YouTube. And you can get an audio-only version on pretty much the major podcasting platforms. In case we're missing a platform, let us know. We'll try to add it. And also, in case you have any ideas for topics that you would like us to cover, let us know, and we'll take them under advisement. No promises. That's it on the second to last day of the year 2023. Bye from the sunny south of Portugal.
Lots of snow even in Helsinki, Finland. Yeah. And it's going to get cold. It's not that cold, but it will get really cold.
Remember, Mick, you're always welcome. You know, if it becomes too cold, just head stop.
Yeah, I think I will be, or we will be doing some sessions from Portugal.
All right.
I'm fairly sure.
Cool. So thanks everybody for listening and viewing. See you next week and Saturday at noon GMT. Till then.
Bye-bye.